Today we will start a new topic, that is diffusion and dispersion. So far when we discussed correlations, I had told you that there are two mechanisms of transport, convection and diffusion. Convection is transport along the direction of fluid flow. Okay. When mass, momentum or energy is carried along with the fluid as it flows, okay, that mechanism of transport. So, when the fluid flow, fluid velocity across a surface results in transport of mass, momentum or energy across the surface, that is called convection. Okay. So, it is directional, it is in the direction of fluid flow. Diffusion is transport of mass, momentum or energy due to the molecular velocity fluctuations. At room temperatures, all molecules have kinetic energy which is equal to, which is given by equipartition of energy in equilibrium thermodynamics. So, all molecules are fluctuating with velocities comparable to the kinetic velocity of the molecules at room temperature. Okay. And if there is no variation in concentration or temperature, right, diffusion is an isotropic process. It takes place, the molecular fluctuating velocities have equal magnitudes in all directions at equilibrium. Okay. So, it is an isotropic process with no preferred direction. If the concentration or the temperature were uniform, this isotropic velocity fluctuation will not result in transport in any one direction, right, because it has equal probability in all directions. So, the probability of energy getting transported from left to right is equal to that from right to left, and therefore, there is no net transport. However, if there is a variation in or a gradient in the concentration or the temperature, then the molecules that transport travel in one direction, they could have a different concentration than those that are traveling in the opposite direction. Okay. And because of that, you could get a transport of mass or energy or momentum along the direction where there is a variation. So, diffusion is an isotropic process, the molecular fluctuating velocities are isotropic, they have no preferred direction, and therefore, transport takes place in the direction where there is a variation of properties, and that is what is called diffusion. Now, if you had a turbulent flow, for example, okay, so for example, if you had a flow in a pipe, okay, which was turbulent, so that you had fluid eddies, okay, circulating in all directions. Okay. Okay. Then there is cross stream transport due to these eddies, which are parcels of fluid in correlated motion. Okay. And this is convective transport. This is taking place along the direction of the fluid velocity fluctuations. Okay. However, if I represent the flow in this turbulent flow in this pipe as the sum of an average flow, okay, the mean flow is along the streamwise direction, okay, plus a fluctuation about that mean. Okay, so that the velocity at each point is described as an average value plus a fluctuation about that value. Okay. The average velocity will transport mass, moment or energy along the direction of flow, along the flow direction, that is convection due to the mean flow. There is also transport in all three directions because of the fluid velocity fluctuations. As I said, in a turbulent flow, the velocity fluctuations are comparable to the flow velocity, and they take place in all three directions. Okay, and therefore, there could be fluid velocity fluctuations in all three directions, and these fluid velocity fluctuations could also transport mass, momentum or energy. This mechanism of transport by the fluid velocity fluctuations is what is called dispersion. Okay. When we separate out the fluid velocity into a mean velocity plus a fluctuating velocity, there is convection due to the mean velocity, which is the mean convection, plus there is convection due to the velocity fluctuations. The velocity fluctuations do not transport energy or mass on average. Okay. Because the velocity itself is 0 on average. So, the velocity fluctuations do not transport fluid mass on average, right, because the velocity is 0 on average. But when there are variations, they can transport species, soluble species concentration or energy, okay, when there are variations in concentration or temperature. And that mechanism is what is called dispersion. Okay. So, we will first look at diffusion and then we will look at dispersion. And the discussion on diffusion will be based upon molecular models for liquids and gases. Okay. Okay. So, we will get the molecular dependencies of the diffusion coefficients in gases using kinetic theory of gases, and I will give you a qualitative discussion of what is this the diffusion in liquids. Okay. So, those will be the two topics in this class. The model that I will use for explaining diffusion in gases is what is called the hard sphere model. Okay. For gases, and the hard sphere model essentially is that the gas molecules can be approximated as hard particles which have no interaction with each other when they are not in contact, and they undergo instantaneous collisions when they are in contact. Okay. Okay. So, they just travel long distances between successive collisions, okay, which is called free flight of the molecules, and when two molecules encounter each other they have an instantaneous collision. Okay. So, basically this means that the time of a collision is very much smaller than the time between collisions. Okay. So, I will assume a hard sphere model with some molecular diameter for these molecules as dm. Okay. And this molecular diameter can be measured in several ways. I will not go into the details here, but for the present we will just assume that there is a specific molecular diameter which depends upon the molecular species. Okay. And based upon this we will see a little later that the diffusion coefficients are proportional to the square root of the absolute temperature. Of course, real molecules are not hard spheres. Okay. Real molecules are not hard spheres, and therefore, they have a nucleus and an electron cloud around them, and the interaction between the two electron clouds of two molecules is not an instantaneous process. Okay. It is a deflection due to these electrostatic forces which takes a finite period of time. Okay. So, this hard sphere molecule is not exact for real molecules. Okay. If you actually calculate the temperature dependence of diffusion coefficient of real molecules, what are called soft sphere molecules, they will increase proportional to a power greater than half for the temperature. Okay. So, in general you will not get the T power half scaling for real gases because they are not exactly hard spheres. Okay. However, for ease of depiction and for discussion, I will assume a hard sphere gas here, and in our case we will see that the diffusion coefficients all scale as the square root of temperature for our present discussion. Okay. If you want more exact estimates, then one has to go to soft sphere molecules and do the calculation for that. That is requires a detailed discussion of kinetic theory, which is not within the scope of this course. Here we will just use a simple hard sphere model and use that for our estimates. Okay. Okay. So, how do we model mass diffusion, okay, for this hard sphere model? Okay, if I consider two chambers filled with two different kinds of molecules, and a barrier between these two is instantaneously opened up, right, then there will be diffusion of one kind of molecules which I will call the A molecules downwards, and diffusion of the other kind, the B molecules upwards. Okay. In gases in general, if the molecular mass is not equal, then there could be motion of the center of mass as well in this case, right, because the molecular masses are not equal. But for simplicity, we will just consider the molecular masses to be equal. Okay. So that there is no motion of center of mass, and we will just consider the motion relative to each other, okay, of the molecules relative to each other, okay, a solute species within this gas. Okay. So, if I expand out, okay, this region, okay, what I have is the separation. Okay. You have molecules of one kind having fluctuating motion here, and molecules of another kind. Okay, and some of these molecules would have diffused across as well. Okay. If I consider the z coordinate as the coordinate perpendicular to the separation, okay, and I plot the concentration of, say, species A across this. Okay. Initially, of course, it will be some kind of a step function because it will be non-zero here and it will be 0 here. As the molecules diffuse across, you will get some kind of a concentration variation here. Okay. You will get some kind of a concentration variation across this. Okay. Now, why does mass diffusion take place? Okay. The reason is because the molecules that are traveling downwards across the surface, okay, the molecules that are traveling downwards across the surface, okay, originate at some point above the surface. Okay. That point is comparable to what is called the mean free path. Okay. Okay. The mean free path is the distance between successive collisions of a molecule. Okay. So, the molecules that are traveling downwards through the surface originate at a point that is approximately that is of the order of a mean free path above the surface. The molecules that are traveling upward at the surface originate at a location that is about one mean free path below the surface. So, the probability of a molecule going down or up at that surface is the same. Okay. However, the concentration at the location 1 mean free path above the surface is greater than the concentration at the location 1 mean free path below the surface, and because of that there is the net transport of molecules, okay, from above to below. Okay. What is the flux of molecules that is coming downwards across the surface? Okay. The flux of molecules that is coming downwards in the z direction, okay, recall that the flux is equal to the velocity perpendicular to the surface times the concentration. Okay. When we did convection, we said that it was equal to the velocity perpendicular to the surface times the concentration at that surface. Okay. So, the velocity perpendicular to the surface will be, okay, proportional to the root mean square velocity. Okay. It will not be exactly equal to the root mean square velocity, but the average velocity of all molecules coming downwards to the surface will be equal to some factor times the root mean square velocity of the molecules at that location. This A is a factor that takes into account the ratio of the average velocity of molecules crossing the surface and the average velocity of all molecules. Okay. So, that is a factor. So, I have written the velocity perpendicular to the surface as a constant factor times the root mean square velocity. This times the value of the concentration not at the location z, but at some location z plus b lambda, okay, where lambda is the mean free path and b lambda is the average location of the molecules that are crossing from above to below. Okay, is the average location of the molecules that are crossing from above to below. Okay. As I said, molecules coming from above to below originate at some location which is approximately one mean free path above the surface. Okay. One can do a similar, okay, formulation for the molecules going from below to above. Is equal to Aj into Vrms into the concentration at some location z minus b lambda. So, for the total flux, okay, if we define the flux in the plus z direction as positive, okay, if we define the flux in the plus z direction as positive, then J z is equal to the flux going above minus the flux coming below, okay, which is equal to A VRMS into C A at z minus B lambda minus C A at z plus B lambda. That is the total flux. Now, the characteristic length scale for diffusion is the length of this tube L. Okay. The characteristic length scale for diffusion is the length of this tube L. Okay. If the continuum approximation applies to this case, that means that the mean free path is much smaller than this characteristic length scale. Okay. If we have to define continuum fields for this case, it means that the mean free path is actually much smaller than the characteristic length scale. Okay. So, therefore, if the mean free path is much smaller, then the derivative, okay, dCA by dz will scale approximately as delta Ca by L, okay, the ratio of the difference in concentration divided by the length. Okay. And therefore, Ca at z plus B lambda, okay, if I expand in a Taylor series, Ca at z plus B lambda dCA by dz at z plus etc. Okay. Let me just add one term here. Okay. Do a Taylor series expansion of this. Okay. You can see that this term scales as B lambda delta C A by Z. Okay. Okay. It scales as B lambda times delta C A by Z. Okay. Okay, B lambda times delta C A by L, and in the continuum limit this term, this factor here lambda by L is small. Okay. Therefore, the second term is much smaller than the first term, the third term is much smaller than the second term, etc., because the next term will go as lambda square by L square, the next term will go as lambda cubed by L cubed, and so on. Okay. So, in this limit I can truncate the Taylor series at just the first term. Okay. So, if I truncate the Taylor series at just the first term and neglect the second and higher terms in the limit where the mean free path is small compared to the macroscopic length scale, okay, the system size L. Okay. The second term goes as lambda by L, the third term goes as lambda square by L square, and so on. And in that limit I can truncate the series at just the linear term, okay, and use that in my expression for the flux. Okay. So, in a similar manner, C A at z minus B lambda is equal to C A at z minus B lambda d C A by d z at z plus etc. Okay. And in here I have the difference between C A at z minus delta z and C A at z, and you can see that when I take the difference between the two, I just get minus 2 B lambda. Okay. So, I will get A VRMS to minus 2 B lambda. Okay. dCA by dZ. This is equal to minus 2AB. Okay, I put an AJ there, so I will just retain that J. So, that is the expression for the flux. Okay. Compare that with Fick's law. Okay. Okay. And you can see that this is the estimate for the diffusion coefficient. Okay. This is the estimate for the diffusion coefficient. This is the molecular expression for the diffusion coefficient. It does contain unknown constants which are order 1, okay. But subject to that, the diffusion coefficient is proportional to the root mean square velocity times the mean free path. Recall that the diffusion coefficient has dimensions of length square per time, okay, and therefore, the mean free path times the root mean square velocity has dimensions of length square per time. Okay. Minus d times dCA by dZ is the differential form of Fick's law that we had used earlier, which was delta Ca by delta Z. Okay. So, if you take the limit as delta Z goes to 0, this becomes a total derivative if there is variation only in the Z direction. Okay. So, that is the estimate for the diffusion coefficient. Okay. So, this is a microscopic expression derivation of Fick's law of diffusion, okay, for a gas. The diffusion coefficient is proportional to the product of the root mean square fluctuating velocity and the mean free path. Okay. Okay. So, let us see if we can estimate the root mean square fluctuating velocity and the mean free path for this diffusion problem. Okay. Okay. First, the root mean square fluctuating velocity. Okay. What is the approximate magnitude of this root mean square fluctuating velocity, okay, in a gas? Okay. From kinetic theory of gases, we know that half m Vrms square is equal to 3 by 2 kBT, okay, where m is the molecular mass, kb is the Boltzmann constant, and T is the temperature. Okay. This root mean square velocity is this equipartition of energy is valid both for liquids and for gases. Okay. For any material at a temperature T, the root mean square velocity has to be given by half mv square is equal to 3 by 2 kT. That is, there is half kT of energy in each translational mode. Okay. This applies both for gases and liquids. The difference is that the molecular separation in gases is much larger than the molecular diameter. The molecular separation in liquids is comparable to the molecular diameter. Okay. So, let us find the estimate for Vrms at 300 Kelvin, okay, for hydrogen and oxygen. Okay. Okay, let us estimate the root mean square velocity for hydrogen and oxygen at 300 Kelvin. Okay. The molecular mass, okay, for the hydrogen, okay, 1 mole is 2 grams. Okay. 1 mole of hydrogen is 2 grams, that is 0.002 kg, 2 into 10 power minus 3 kg. Okay. That is 1 mole. It contains 6.023 into 10 power 23 molecules. Okay. 1 mole contains 6.023 into 10 power 23 molecules, and it is equal to 2 grams. A kilomole contains 6.023 into 10 power 26 molecules and is equal to 2 kilograms. Okay. So, you get the same mass of the molecule in either calculation. Okay. You can divide this and you will get this is equal to 3.32 into 10 power minus 27 kg. Okay. That is the mass of one molecule. Okay. From this, Vrms is equal to square root of 3 kBT by m, okay, which is equal to 3 into the Boltzmann constant 1.38 into 10 power minus 23 joules per Kelvin. Okay. In this case, we will use Kelvin because when you do kinetic theory calculations, one has to use the absolute temperature. The temperature in thermodynamics in equipartition of energy is the absolute temperature. Okay. So, it is equal to 3 into 1.3 into 10 power minus 23 joules per Kelvin into 300 Kelvin, okay, divided by 3.32 into 10 power minus 27 kg under root of the whole thing, okay, the square root of the whole thing. And you can easily do this calculation, you will get about 1934 meters per second. Okay. kBT is an energy, energy by mass has dimensions of length square per time square, okay, L square t to the minus 2. Okay. So, the square root of that is a velocity. So, this is approximately the speed the root mean square velocity in hydrogen, okay, for hydrogen. Okay. For oxygen, the mass of oxygen is equal to 32, right. So, it is 0.032 kg by 6.023 into 10 power 23. Okay. This is about 16 times, it is 16 times the mass of a hydrogen molecule. The mass of an oxygen molecule is 16 times the mass of hydrogen molecule. Therefore, the root mean square velocity goes as 1 over square root of m. Okay. So, therefore, the root mean square velocity of oxygen Vrms is equal to that for hydrogen divided by 4, okay, and this comes out to about 484 meters per second. Okay. And air, for example, is a combination of oxygen and nitrogen in about 80 to 20% ratio, and therefore, its molecular mass will be 29 instead of 32, and the root mean square velocity will be approximately the same, okay, for oxygen as well. Okay. So, and both of these mean square velocities are comparable to what is called the speed of sound in gases. Okay. Sound is a pressure wave. Okay. Sound is a pressure wave which travels at a speed that is approximately of the same magnitude as the molecular velocity. Okay. Sound travels at a velocity that is close to the molecular velocity. In case of the speed of sound is equal to 1290 meters per second in H2 and it is equal to 330 meters per second in air. Okay. And you can see that these are of the same magnitudes. Okay. These are of the same magnitudes. Okay. So, the speed of a molecule and the speed of sound are approximately of the same magnitudes, and they are about 1000 meters per second in small molecular weight gases like hydrogen, approximately 300 to 500 meters per second in gases like oxygen, nitrogen and so on, and in air, and that is comparable to the speed of sound in air. Okay. So, this is an estimate for the root mean square of the fluctuating velocity. The diffusion coefficient that we had calculated here contains two parts. One is the root mean square of the fluctuating velocity and the other is the mean free path. Okay. So, we will estimate in the next lecture the mean free path and from that we will finally get an estimate for the diffusion coefficients in gases under normal conditions of temperature and pressure using kinetic theory of gases. Okay. So, that estimate for the diffusion coefficient will be used in Fick's law, okay, to actually calculate the fluxes. I will continue this in the next lecture. I will see you then.